Now, in OSPF, we learned that it sends hello packet every 10 seconds, and the wait time is 40 seconds. We saw OSPF hello packets carry a lot of information in which few parameters must match. And then we saw in a serial link, there will be full adjacency. In a broadcast, in a LAN, in a multi-point environment, there's going to be DR-BDR election, and the neighbors are having full adjacency only with the DRs. When I say DRs, it includes BDR. With the other routers, it will have two-way relationship. We'll talk about this in much detail in coming classes. And also we saw how the LSDB, the database, gets built. On successfully forming neighbor, the routers will start sharing their database in a summarized way. That is how the DBD gets built, LSDB gets built. We also saw sequence number matters. It was our last page actually, the flow chart. When a packet is received, it checks whether the database is empty. If it is empty, it copies the update that comes in into the database. If it is not empty, it will check whether the incoming sequence number is bigger than the one which is local. If the incoming sequence number update with the incoming sequence number higher comes in, it learns it into the database and sends an acknowledgement. If it is lower, instead of learning it because it's an outdated one, it updates the sender with the actual info. So all these things we learned in our class. In this chapter, named as Configuring OSPF, we will learn how to configure OSPF. There are two different ways in which you can configure OSPF. And also, we will be learning about packet types in OSPF. Why do we need to know the packet types? So that when we want to check something, we will know what packet to capture. Troubleshooting using the Wireshark is a smart way of troubleshooting. So we can create a OSPF profile in Wireshark, and for each packet type, we can create a button, and we can do a click and troubleshoot. That's really a wonderful thing. So knowing the packet types in OSPF will give us a better understanding about OSPF and help us to troubleshoot well. Let's get into this chapter. See, these are the 5 packet types we have. Hello packet is type 1. hello packet. Now this is the packet that you will be seeing very often when you debug or when you capture using Wireshark, because every 10 seconds this is going to be sent. If it is non-broadcast type, it is not going to be 10 seconds, it is going to be 30 seconds. We'll talk about that later again, but in general, hello packets are 10 seconds. 10 seconds. Only in the case of non-broadcast, hello packets are sent every 30 seconds. Now we are not dealing with non-broadcast. As I said, we'll deal with it later. Now these hello packets are tiny and has got some bunch of information in it, in which few informations must match with a neighbor, others need not to match. The second packet type is database description, DBD. Database description is actually the database getting shared from one OSPF router to another neighbor OSPF router. The database is getting shared. That's why it is database description. It's an update, but we don't call it as an update. We have another type 4 as an update. We call it as database description. Actually, it is LSDB getting shared, link state database shared from one router to another. So when you want to check what is being shared, you need to capture a DBD packet. Now, why do we call this database description DBD? Why not LSDB? Actually, LSDB is what we share here. LSDB is what shared in this packet. Then why is it called as DBD? Why it is called as DBD? Why not LSDB? The difference is this. The summarized form of LSDB is what the routers will send between neighbor. The summarized form has got a name called DBD. LSDB is very detailed. Detailed information is not actually shared because it will take a lot of CPU as well as bandwidth. You remember in the last summary slide in the previous chapter, we learned that not only during the neighborship it shares the DBD, it also synchronizes every time, every 30 minutes. Every 30 minutes, they resend the DBD. They said they want to synchronize. Yes, 30 minutes. It's not 30 seconds. So this DBD needs to be sent, not the LSDB, because it is sent often every 30 minutes. That's going to take a lot of bandwidth and processor if a detailed LSDB is sent. That's why OSPF is designed to send a summary of it. That is actually enough. It shares almost the complete information in a summarized way. Now, because the DBD is being shared, there may be some queries from the receiver. So what receiver does is he sends a link state request asking, may I have a more in detail information for this particular link state. That is what called as LSR, link state request. It's a query. After receiving DBD, the doubts is what called as LSR. See, when we tell a story, when I tell a story like last 20 years, I have been a freelancer and God was taking care of all my needs, though I am not working in an organization, getting paycheck every month, even though I am not working under any organization. God, who has got a very good plan for my future, has taken care of me very well. So well. He carried me this far. Yeah, there are some times when I did not get project and I couldn't make good money. It was a struggle in the beginning, but I was patient, waiting for God to make my path. And He really made my path clear. When I say in a summarized way, people will have question. What? He did not work under an organization for 20 years? He's an independent guy? He's a freelancer? How is that possible in an IT field? We work in an organization month to month, we get salary, but still we are not happy. How can this guy be happy? Having such a big degree, big certifications, and not working under an organization. Self-dependent. So they want to ask question. They are very curious. They want to ask a question. How is that possible? No, we can't believe you. We cannot believe you. How can you do that? I say, yes, it's not me. It's the one who has got my future in his hand. It's God. That is what LSU. So when I send a DVD, they get queries. They ask question. That is LSR. And I respond with a right answer, and which is LSU, link state update. Now, for all these three, no, acknowledgement will be sent. For all these three, acknowledgement is going to be sent. When someone sends DBD, LSAC will go. This is not LSA, this is LSAC. And then when someone sends LSR, LSAC will say, I received your LSR. When a reply has been sent, LSU, the receiver will say, I got your update. That is what LSAC. For hello, we don't send any LSAC. Hello is hello. There is no need for acknowledgement for that. But for other three, acknowledgement is always sent. DBD, LSR, LSU. Acknowledgement is always sent. Now, OSPF packet, when you capture, you will see these fields. Only this portion will vary from one type to another type. For example, hello package won't carry much data. Not much, very less. Whereas this DBD will have a lot of data. So for DBD, this field will have a lot of information. But the other fields, they are common for all packet types. Did you understand what I'm saying? What I have? So the first field is a version number. It is always version 2. The IPv4 version, no, is version 2. OSPF that we are running is version 2 OSPF. If you are switching to IPv6 OSPF, then it will be version 3 here. Let me show you that. See, we have router 6. This is running OSPF. I want to show you that. Show IP OSPF interface brief. You can see OSPF is running on F01. So definitely there is going to be a hello packet sent and received. I want to say debug IP OSPF packets. So it's going to show you all the packets, and I'll just stop the debug as soon as I get 1 or 2 debug packets, 1 or 2 logs. I'm waiting for some packet to come. It won't take this long. If it is taking this long, then there is some issue. Let me go to router 1. Okay. I can see the wire is connected to the wrong interface, F00. It should be connected to F01. Okay. Now I am expecting, you see, as soon as I connect on F01, version 2, you see, this is what I was talking about, version 2. Version 2 is the IP version of, IPv4 version of OSPF. What is this T? Type 1. We saw there are 5 types. Type 1 is what? Hello packet. And the next is length. Length is 44 bytes. Router ID. This is the router ID of that router. Of what? Of the one which is sending this. Actually, it is R1's router ID. What area it belong to? It belong to area 100. You see, area 100. Checksum value, it is for the integrity. Authentication, no authentication. No acknowledgement. And this is the hello received from R1 on F01 interface. All right, so let me stop this and take you back to the presentation. So we just saw these fields. We saw version 2. We saw type 1. Type 1 means what? This hello packet. Type 1. And then we saw packet length, router ID, area ID, checksum value, authentication type, authentication string. And we saw, we didn't see data there because it's hello packet. Fine. Now, this is about hello packet in detail. A neighborship happens through hello packet. First of all, the routers need to identify the neighbor with which it can share the updates. Yeah. So the hello packets are carrying all this information that helps to identify the right neighbor. What all informations? Every router will have a unique router ID. So it should be unique. It cannot be same with other router. Secondly, every router has got a timer, and the default timer is 10 and 40. If you don't change it, it is okay. If you change it, you have to change on every router. Why? This timer should match. The timer should match. Wherever you have that star, no, they should match. Thirdly, the list of neighbors will be shared. Area ID will be shared. The area ID also should match. See, so far two things we have seen that should match. One is timers. The other one is area ID. So area ID should match and timer should match. Okay, the other things are like priority, router ID, DRIP address, BDR IP address, and then authentication, and then stub. All these are shared. In which what all should share? Sorry, what all should match? The timer should match, the area ID should match, the authentication should match, and the stub should match. Stub type should match. Yep. Now, when these are matching, then two router can easily form neighbor. So what should not match is very important. What should not match is router ID should not match. Router ID should not match. There is also one more thing should match called subnet. It is not mentioned here, but it should match. This all are sent in hello packets. Now this is something important to understand. Now we are trying to learn different state the routers undergo while forming neighbor. A and B wants to form neighbor. Initially, it is in down state because you just configured. And one of these routers is sending hello packet. Say, for example, router A is sending hello packet here. In the hello packet, you know there will be a router ID. So in this example here, 172.16.5.1 is the router ID. Router A is sending hello. And it is also saying I don't have any neighbor. It says I see no one. And you see the hello packet is sent to the multicast address 224.0.0.5. It's a mistake there they have done. It's not 244, it is 224. Okay, so now A is sending this to initiate the neighbor. That is why it is called as init state, INIT, init state. Now B receives this because B is running OSPF, it will receive. All the routers that runs OSPF will receive packet that are sent to 224.0.0.5. I repeat, all the routers that run OSPF will receive, will process the packet that are sent to 224.0.0.5. So B processes it and B learns a neighbor called 172.16.5.1. So B learns about a neighbor which is router A. To that neighbor, B is sending a unicast packet saying, hey neighbor, this is my hello, and I have a neighbor in my list. Now when this goes, router A can see its own address as a neighbor of B. That makes router A to understand that I know B now, B already know me, so we are in two-way state. We are in two-way state. I know him now, and he already know me, which means we know each other two-way state. After this, they are going to now share the update, but both cannot share at the same time, no? One should share, other should receive. So what happens? Between these two routers, they come to a conclusion who will share first and who will receive. Who will share first and who will receive. Okay, who will share first and who will receive? Now, Router A says, I want to share. And router B says, no. See, no. I will start sharing. Why? Because my router ID is bigger. This decision is what made in this place called XStart state. Exchange start. To start the exchange, they need to come to a conclusion. They need to take a decision like this. So router B will now start the exchange called DBD. See, it is not sending the LSDB. It is sending the summary of LSDB. That's what I called it. We call it as DBD. DBD is type 2 LSA. DBD is type 2, not LSA. Type 2 OSPF message type. OSPF message type. We don't call this as LSA. It is called as message type. Message types in OSPF. Type 2 is DBD. Is that clear? Okay. Now, the other router says, okay, fine, I received it, and this is my DBD. So they both exchange the DBD in a state called exchange state. They exchange the DBD. And now comes the loading state. What is loading state? After they receive the DBD, they share the acknowledgement. After DBD exchange, they share the acknowledgement for that. And then the queries I was telling, LSR and LSU, which is called as loading state. Queries. They asked out about more information. See, here it is written. I need a complete entry of network 172.16.06.0. I want a complete entry. See, it's querying actually. It's called LSR message type. And for that, LSU will be sent. And this is what we call it as loading state. After that, they again share the acknowledgement and they form full adjacency. See, neighborship is already formed when the two-way state. Neighbor state is formed right here itself. I know him, he know me. But after that, the exchange and all happens. No, this is what called as adjacency, full adjacency. So there are 7 states you see here. Init state, and then two-way state. No, first it was down state, and then init state, and then two-way state. This is where the neighbor got established. And now they decide whether I should start the exchange or the other guy should start the exchange. So that decision, the DR, BDR election, all this stuff happens in the start state. DR, BDR election. If it is LAN, DR, BDR election. If it is WAN, if it is serial wire, then it is going to be something called master slave. So those decisions are made in the start state. When we do the lab, I'll show you in the debug. Fine. They come to a conclusion who will start the exchange. And then in the exchange state only, they give the DBD. And then followed by acknowledgement. Afterwards, the loading state is they send a query and response comes, LSR and LSC. Acknowledgement at last is sent to say that we are fully synchronized. These are the 7 stages: init, two-way, extract, exchange, loading, and full. Including the down, we call it as 7 state: down state, init state, two-way state, extract state, exchange state, loading state, full state. Yeah. Okay. In a multi-point environment, what is multi-point environment? When we have more than 2 routers in a LAN forming neighbor, definitely there will be a switch involved in it. There is going to be a switch to connect more than 2 devices, right? So this is the line that explains the switch. to the switch, when you connect 4 router, definitely the 4 router is going to be in same subnet because switch means it's layer 2. If the IP address here is 10.0.0.10, this also will be in 10.0.0, maybe 1. This is 10.0.0.2. This is 10.0.0.3. All are in 10 network. Only then you can have a switch in the middle. Now, whenever we have more than 2 router to form neighbor, there will be a DR-BDR election. There is going to be a DR-BDR election. The router with a higher priority becomes designated router. The second highest will become backup designated router. Why do we need this? We need this to avoid duplication of update. We need this to prevent loop. Yeah. So we are going to have a DR and a BDR. If the priority is same, by default the priority is 1 on all the LAN interfaces. The default priority when you enable Ospf is going to be 1. In the hello packet, even the priorities are shared. The priority is 1. Only when you increase the priority, the router becomes DR. If you don't increase, if the priority is default, using the hello packets, one router will know about the router ID of another router. So what they do is they compare the router ID and now they take a decision who should be a DR. Let's say the router ID of this one is 5.5.5.5 because the loopback interface has got that address. And this one is, let's say, 4.4.4.4. And the other one is 1.1.1.1, 2.2. So this becomes DR because of the higher router ID. The other one becomes BDR because this is having the next highest router ID. Fine. What is the specialty of DR and BDR? What is the specialty of DR and BDR? When we enable OSPF, usually every router will be listening to the address 224.0.0.5, but the DR and BDR will be listening to 224.0.0.6. Yeah. DR and BDR will be listening to 224.0.0.6. And rest all will be listening to 5. So when any update need to be sent, say for example, A has lost a link, it want to update. It will update to 224.0.0.6. So only DR and BDR can receive it. Only DR and BDR can receive it. No one else can receive it. When a packet is sent to 224.0.0.6, those two routers which is listening to the 224.0.0.6 only can receive it, which means DR and BDR can receive it. No one else. Now, DR will be using 224.0.0.5 to send it. So all will be receiving from DR, not from A. A will not directly send to all. A will only form full adjacency with DR. A will not form full adjacency with other. One other will not form adjacency with other. all other routers will form full adjacency with the DR and BDR only. So whenever there is a change, the other router will not send to all other routers, it will send only to DRs. DR will collect it and update to rest of the other routers. In this way, duplication of update loop is prevented. So this is the idea. When an update is sent to 224.0.0.6, only DR can learn it. DR and BDR can learn it. When I say DR, it includes BDR. Only DR can learn it. And BDR will not send any update. DR only will update all other router using 224.0.0. Fine. So this is address from DR. This is address to DR. To DR, what is address? What is address? 224.0.0.6. From DR, what is the address? 224.0.0.5. Did you understand this? From to DR to 224.0.0.6 is what used. Is it correct? No. You're not listening. You're not responding also. Please respond. Yes. Any update sent from DR will be using 224.0.0.5. Any update to DR will be notified using 224.0.0.6. Now, if you talk about the other routers, it is opposite. To DR, it will use 6. To the DR, if they want to send anything, they will be using 224.0.0.6. And if they want to learn from DR, it will be using 5 to learn from DR. No, that's the other way of saying the same thing. Okay, now let's read what they have written here. Router A notifies to DRs, yes, to DR. DR notifies using 5. Is this clearly understood? Okay. I think about the sequence number, we will see